welcome in lecture fact. And first of all, just we'll take the review of variable impedance type controllers. Shunt compensation. In the shunt compensation, first we saw the thyristor control reactor and thyristor switch reactor. So here, this is the example of a thyristor control reactor. In the thyristor control reactor, this is the thyristor whose current we are going to vary. That is the current I, and it is the function of firing angle alpha. And two thyristor walls are connected in the bidirectional. Already, since we have discussed that the one thyristor may vary, may carry the rating of the one thyristor is maybe 4K to 9K. So number of thyristors are connected in series to obtain the required voltage level. Similarly, the one thyristor may handle up to the 3 to 6 kilo ampere. So as per the current rating, we are connecting the number of thyristors in parallel, and the total is called as a thyristor wall are there. Now, this is the system voltage, the voltage which we have here, that is the voltage V, and this is the waveform for the voltage. Now, if the thyristor is fired with the help of gate wall without any delay, means the delay angle is equal to 0, it is going to conduct, this is positive half cycle, there is no delay. And if there is a delay, if the delay angle is alpha, so the amount of current or the quantity of current get decreases. So it is simple to say that the amount of current in the inductor can be varied with the help of changing the firing angle. 0 firing angle, 100% conduct. There is a increase in delay angle, the amount of current decreases, or the conduction angle decreases over this one. So this is the conduction angle and this is the firing angle. Now, this is same for the negative half cycle. And in this diagram C, this is the system voltage. This is the system voltage. Here, there is no delay in the firing angle. So the amount of current is large. In the negative half cycle, the firing angle alpha is equal to alpha 1. So this is the firing angle. So amount of current get decreases. In next consecutive cycle, half cycle, the firing angle again increases. So there is a delay angle is increases. You can say that say delay angle. So delay angle is increases. This is the delay angle over this one. So under such condition, the conduction angle is smaller and so on. So we found that by increasing that angle, the amount of current decreases. So this is the control over the reactor value by proper firing of thyristor wall. This is the case for the thyristor controlled reactor. Now, if the thyristor, now see here, this is the very important points. The thyristor firing angle, the range of this firing angle is from 0 to 90 degree. Says from here to up to this one. Okay, up to this one. So this is the we can vary up to this one. So we can vary the angle. So when we are varying this angle, if suppose the firing angle that alpha is equal to here, it means that the reactor is off. Here the reactor is on. If you are firing the reactor, if you are firing this thyristor, so there is a full conduction. If you are firing at this point or this point, the firing angle is equal to 0 and the conduction become 0. So therefore, you can make, or one can make, the thyristor controlled reactor, where the reactor current is possible to control is the thyristor control by changing the angle alpha. If the angle alpha is equal to 0 or alpha is equal to 90, under such condition, the conduction becomes 0 and it becomes thyristor switch reactor. So this is the review of the first part. So our angle of the conduction can be varied. Now, second case. Now for this one, this is the thyristor control reactor. This is thyristor control reactor, and this is the conduction area or operating area, where it is possible to change the firing angle and change the reactive power absorption. There's a change in reactive power absorption with the help of change in firing angle. So this is the boundary where we can control the reactive power absorption, because the reactor is there, so it is the absorption of the reactive power, and when there is a capacitor, then generation of the reactive power, means it is going to deliver the reactive power to the transmission line, and if the reactor is connected, it is going to consume the reactive power from the transmission line. Now this is the VI characteristic or VI area, operating area for the thyristor switch reactor, because we are switching the thyristor either conducting or not conducting. So this is the not conducting points. It is not conducting and it is going to conduct to its maximum value. So this is governed by the system voltage and current, maximum current capacity of thyristor as well as the walls are there. So this is the difference. This area hashes, this lines indicate that entire area where we can operate in this region, we can operate our thyristor control reactor. Now thyristor switched. Thyristor switch capacitor. So in thyristor switch capacitor, this is the diagram. This is the system voltage V. This is the capacitor whose capacitive reactance, capacitive current is going to control with the help of thyristor walls, similar to last, which already explained. And one inductor, limiting current inductor, is introduced to limit the that current, as well as it avoid the resonance in the system. So here the important point is the instant of the switching of the capacitor. If we are switching the capacitor at any value, definitely there is a transient in the switching. So it will occur the switching transient because of the capacitor. Okay. So when the switch is on, means the thyristor is conducting, these thyristors are conducting. So over this one, the capacitor, the voltage across the capacitor is equal to the voltage across the system, and it is charged. Either it is going to charge to the positive direction, and either it is going to charge in the negative half cycle, positive half cycle or negative half cycle. But if you next time when you are going to switch on the thyristors, there may be some condition. The first condition is that charged capacitor is equal to or less than equal to the supply voltage. And the second case, the charged capacitor definitely is the previous charging history. The charge capacitor voltage is less than the system voltage. Sorry, the charge capacitor voltage is greater than the system voltage. So under such condition, this is the system voltage, this is the system voltage, and this is the charge capacitor value, which is equal to or less than the system voltage, the intersection point is the correct position where the thyristor should be triggered in such a way that it will give the transient free switching. Similarly, when the capacitor charged voltage is greater than the system voltage, the maximum value of voltage, or we can say that dV upon dt is 0. Under such condition, the switching is a transient free. This can be explained very well with the help of this diagram. Say, for example, over here, this is the system voltage. This is the system voltage, and this is the current in the capacitor, or the current over which is going to flow in the capacitor to produce the capacitive reactance and supply to the system. Okay. Now here the current is leading one. The current is leading because during this time the voltage is equal to negative maximum, and so it is leading. Now here, this is the voltage drop across the inductor. So a small voltage drop into the inductor. Now at this point, the capacitor, is turned off. The SCRs, the valves are, thyristor valves are turned off. So during turn off, the voltage across capacitor or charge voltage of the capacitor is this much, isn't it? So this is the meaning for the charge capacitor which we have discussed. Now this is the condition for the transient free operation of the thyristor switch reactor. Say this is the system voltage. This is the charge capacitor voltage which is equal to the system voltage. So what is the correct instant to start the capacitor to switch on the thyristor valve? It is the intersection of system voltage and charge capacitor, or here it is the maximum point. So when we are starting or we are conducting the capacitor, the current in the capacitor is sinusoidal and it is transient free. So this is the positive charge, positively charge the capacitor. Now similarly, the charge capacitor is up to the maximum to its system voltage, but in the negative direction. So this is the instant, this is the right instant to turn on the thyristor, and as soon as the thyristors are turned on, again it will give the transient free switching of the capacitor. Next, this is the case where the capacitor is fully discharged. Now your capacitor charge voltage is equal to 0. Under such condition, if the thyristor is turned on, this is the waveform of current. So it will give the transient, and after 1.5 cycle, it is going to settle. So this is the case when the capacitor charge voltage is equal to 0 and the thyristor is turned on. So there is a large transient, and after 1.5 cycle, it is now settled to its normal position. And as soon as we turn off the capacitor, here the thyristor is turned off. After turn off, again the capacitor voltage or charge voltage is VC. Similarly, this is the case when the charge voltage of capacitor is equal to 0.5 pu. Whatever the rated voltage is there, it is the 50% is charged. So under such condition, the current is this is the current of the capacitor, and it is found that the transient is smaller. So there's a one conclusion is that the transient free operation or transient free switching of the transistor capacitor is either this is the one point we can operate, we can start the turning on the thyristor. It may be this way, this one, isn't it? Or this one is there, isn't it? So as the switching of the transient capacitor, it may be complete half cycle or it may be a full cycle. So it is not the thyristor controlled reactor because we are not able to turn on the thyristor to conduct the capacitor. Therefore, only thyristor, this is thyristor control capacitor will not be there. It is thyristor switch capacitors are there. So this will not be there, only thyristor switch. Either it is going to conduct its a full capacity or otherwise it will stop or not conduct. So this is the case. So here there is no hashing area is defined or the area it is not defined. So it is not a control area. Either it is going to conduct to its maximum capacity or otherwise it will be zero. So this is the difference between thyristor control reactor and thyristor switch capacitor. Now, for today's topic is the fixed capacitor thyristor control reactor type VAR generation. So it is discussed that in the limitation of thyristor switch capacitor, either it is going to conduct its rated value or otherwise it will stop. To control the value of capacitor, to control the VAR generation or delivering to the system, it can be done by controlling the reactor along with the fixed capacitor. So see, this is the system voltage. The value of capacitor is remain connected. So this is the constant value of the capacitor. Whereas the current in the reactor is controlled by change in firing angle. So as soon as the firing angle is going to change, the total reactive power, which is the combination of capacitive reactive power and inductive reactive power, because both are opposite to each other, the equivalent or the total power is going to deliver to the system or either absorption or either say generation of the reactive power. So this part is a thyristor control reactor and it is a fixed capacitor. So the combination of this one, it become a fixed capacitor thyristor control reactor is there. Now as the operation, independent operation already explained. So it just we come to the its next point directly without explaining again the individual one. This is the total capacitance reactive power QC, which is equal to V multiplied by IC. Since it is permanently connected, fixed, it is connected fixed over this one. Whereas the reactive power, which is the function of current, and again the current into the reactor is depend upon the thyristor, it depend upon the firing angle. If the firing angle increases, the current in the reactor get decreases. Again, I will say, as the firing angle increases, the current in the reactor get decreases, and the effective compensation is the capacitive compensation. And if the thyristor is fired at alpha is equal to 0, the reactor handles maximum its rated current. Under such condition, it absorbs the reactive power, or we can say that the compensation is an inductive reactance. Clear? So let we assume that the inductive reactance, inductive VAR is greater than the capacitive VAR. So if thyristor is conducted at alpha is equal to 0, means it is simply switch on, there is an absorption. So it can be explained with the help of VI characteristic or VI area. Since the capacitor is a thyristor switch capacitor, where we found that in the previous condition, there is no control area. But in conjunction with the thyristor control reactor, the effective value of entire means total fixed capacitor thyristor control reactor can be VAR can be controlled. At this position, at this, say for example, at this position, we can say that the VAR, capacitive VAR and inductive VARs are equal and opposite. So the fixed capacitor thyristor control reactor neither generating the reactive power nor absorbing the reactive power. It's just floating. Whereas if the current in the reactor is greater, more means its full value, the total effective compensation is an inductive compensation, means it is going to consume or absorb the reactive power. Whereas in some value, either some value over here, we can say that the fixed capacitor inductive power is greater and it is going to generate the shunt compensation, or it is going to generate the reactive power and deliver to the system. So this is the operation of single fixed capacitor. Now, as this is the fixed capacitor, it is possible to have a number of capacitors in the system. Say for example, there are, we can make it thyristor switch capacitor, isn't it? This is not a thyristor switch, it is a fixed capacitor over here. So we can make thyristor switch capacitor, thyristor control reactor. Means one part is a thyristor control reactor and one part is a thyristor switch reactor. So this is the case. Here, the number of capacitor C1, C2, C3 are connected in parallel with their individual control 1, switch 1, switch 2, switch 3 and switch 4 and so on. No doubt it is connected with the some inductor for the limiting current and to avoid the resonance. Now here this is the smooth control, and whereas it is in the step control. In the previous case, it is not possible to control the capacitor current or capacitor over this one, but here it is going to control, but it is in step manner, and whereas the inductor in smooth manner. So the VI characteristic, it is shown only for the two. It may be 3 or 4. So this is one, say this is the C1 is there, then C2 is there, then it is C3 is there. So this is in the switching manner, and whereas the thyristor, this part is thyristor control reactor, it is in the smooth manner, as it is for the thyristor switch capacitor 1, thyristor switch capacitor 2 and so on. So by this way, it is possible to control the compensation either by thyristor switch capacitor or thyristor switch reactor and thyristor control reactor. So in the next time, we will see the second part, that is switching converter type VAR generation. So first part is the converter which is used for the different impedance. We are controlling the impedance of the shunt compensation. And in the next time, we will see the method of changing the impedance by the switching type. Thank you.